In this video, you're going to get a lot more practice calculating the pH of acids. But wait, not just acids, mixtures of acids. For our first example, we're going to look at a mixture of a strong acid with another strong acid. So we'll start by doing this problem here. First, you need to think about the scenario given in the problem. In this scenario, we're going to pour together two different acids into the same container. So what happens to the volume of the solution? Well, the volume of the solution is a total of 300 milliliters. What does that mean happens to the concentrations? Well, the concentrations are going to change because the volume changed. As you look at what we have in solution, we have hydrochloric acid, a strong acid, and hydrobromic acid, a strong acid. So if we were to make a major species list, we would get water, our solvent, hydrogen ions from both acids, bromide ions, and chloride ions. Our interest lies in the hydrogen ions because that's what will give us the pH. Now that we've identified what we have in our solution, we need a strategy. Well, to get the pH, we need to know the H+ concentration. And to get the H+ concentration, we need to know the moles of hydrogen ion and the volume of the solution. Good news, we already have the volume of the solution. All we need is the moles of hydrogen ion. We have two sources of hydrogen ion. We have the HCl and the HBr. So using each one, the molarity times the volume of each one will give us moles of hydrogen ion. Do that for both of them. We can easily get the total now. That's a total of 0.021 moles of hydrogen ion. Take that with our total volume of 0.3 liters, and we have the molarity. That gives a molarity of hydrogen ion of 0.07 molar. And you know what to do to get the pH. So we have a pH of 1.15. For sig figs, I go back to my original problem, and I see 4 sig figs, 2 sig figs, 4 sig figs, and 2 sig figs. I've done a whole bunch of multiplication, maybe a little addition here, and that boils down to an answer of 2 decimal places in the pH to correspond with our 2 sig figs in the molarity. Okay, that's one problem down, 2 to go. Next, we're going to look at a strong acid mixed with a weak acid. In this kind of problem, your major species list becomes very helpful. So let's list what we have. We have water. We have a strong acid right here, so that gives us hydrogen ions and nitrate ions, because that's what strong acids do. We have a weak acid here, and since weak acids do not ionize a lot, we shall keep it together. So we have acetic acid. Now we have a complete major species list. We can talk about what's going on in the solution. Just like in the last problem, we have two sources of hydrogen ion. We have the strong acid, which gives us hydrogen ion right off the bat, and we have the weak acid, which gives us some more hydrogen ion as it dissociates, ionizes. So the first thing we're going to do is talk a little bit about this weak acid equilibrium. So let's do this equilibrium problem for our weak acid and see where that takes us. For our initial amount of the weak acid, that's going to come from our given amount of 0.05 molar. We have some initial H+. It's in our major species list, and it's got to be jumping up and down at you saying, I'm here, look, I'm right here. That comes from our strong acid. So our initial amount of H+ is 0.05 molar. And our initial amount of the acetate ion is 0 because we don't have any in our major species list. So we finish our ice table, and then let's plug everything into the Ka expression and see where that takes us. So we get this right here. And you think, oh, how am I going to solve this? Oh, wait a minute, I know the drill. K is very small. And since K is small, the equilibrium lies to the left. But the change is going the other way, to the right. So therefore, X is very small. So when we add or subtract X, we can ignore it. Look at how easy this one is to solve now. I don't even need a calculator. I know that X equals 1.8 times 10 to the negative fifth. Okay, so we solved for X, and I even checked to make sure the assumption was good, and we're way under 5%. And now we can look at what we have here. This time, X is not the H+ concentration. Rather, X is much smaller than the H+ concentration. Oh my gosh! So this means that the H+ concentration is actually 0.050 molar. Do you realize where that came from? That came from our strong acid. The strong acid totally dominated the pH because it totally controlled the hydrogen ion concentration. The weak acid really didn't do all that much to help. So the pH of this solution is the same as the pH of a solution of just our 0.05 molar nitric acid. Again, that's because this weak acid doesn't do much to contribute to the hydrogen ion concentration, at least not compared to the strong acid. So the moral of the story is, when you have a mixture of a strong and a weak acid, the one you need to focus on is the strong acid. That's the one that's going to dominate the pH and control the hydrogen ion concentration. What does that mean? In the future, you don't have to bother with all this weak acid equilibrium if there's also a strong acid present. I just want to review a couple of comparisons with the previous problems. First of all, in the previous problem, we had two strong acids, and they both added to the hydrogen ion concentration, so we had to calculate both of them. In this problem, we have a strong acid, so our hydrogen ion concentration is coming from there. And we have a weak acid, so when we did the equilibrium, that's where that concentration came from. Another difference is, the first problem involved combining two solutions, so we had a volume change. This problem is worded a little differently. We don't have two solutions that we're pouring together. We just have two different things already in the same solution, so we did not need to worry about any volume changes. Phew, that's two problems down, one to go. I bet you can guess what we're going to do next. Let's see. We did a strong acid plus a strong acid. Then we did a strong acid plus a weak acid. Seems to me that the only combination left is going to be two weak acids mixed together. If we look at our major species list, in this case, we have water, of course, our solvent. We have a weak acid, HCN, keep it together. And we have another weak acid, acetic acid, keep that together, because weak acids do not ionize very much. Gee, I wonder what we should do. It looks like a complicated equilibrium problem. Hey, I know. Let's use what we learned in the previous problem to see if we can make a good prediction about what might happen in this problem. Of these two weak acids, Which one is stronger? Let's see, we have Ka equal to 1.8 times 10 to the negative fifth versus Ka equal to 6.2 times 10 to the negative 10th. Aha! The stronger acid here is the acetic acid. So let's take a look at that equilibrium first. I'm going to abbreviate acetic acid as HA because it's much simpler to write. So what I have here is the acetic acid equilibrium, and for the initial concentration of acetic acid, 0.2 molar, I took that straight from the problem. The initial concentration of H plus is actually not really zero, because water will give us a little bit of H plus, and HCN will also give us a little bit of H plus. But because HCN is such a weak acid compared to our acetic acid, we can probably ignore it. In fact, we can ignore how much H plus it gives. Same thing with the water. It's pretty weak as far as acids go, so it's not going to do much. So let's carry out the Ka expression and the calculation for acetic acid. Okay, so we plug everything in. We see that K is small, we can ignore X, and we solve for X. And we get X equals 0.0019, and X this time corresponds directly to our hydrogen ion concentration. You can see I checked my value of X, or my assumption to ignore X, and I got 0.95%. That's good to go. And since X is the H plus concentration, I can calculate the pH by taking the negative log of my H plus concentration, and I get pH equals 2.72. You don't actually ever have to calculate the pH of a mixture of two weak acids in which you can't ignore the weaker one. You will only encounter problems like this. Phew, that's a relief, because they get pretty nasty otherwise. All right, so I hope you learned something in this video, and good luck in all your problem solving.